Okay, so we left off last time and we hadn't completed all the slides, so I'm gonna start our video conferencing by going over these last couple slides that we didn't cover from section 9.2. We did go over this very important theorem that's going to help us out quite a bit, and it says that if your if your series converges, then your terms have to be going to zero. So it should be relatively intuitive that if you're adding an infinite number of terms, that if the terms are not going to zero, then your series has no chance of converging. It's also not the case that just because your terms are going to zero, then your series has to converge. We have the harmonic series as a counterexample to that. But we do know then, people confuse this theorem all the time. This says if it converges, then your terms have to go to zero. And so then if your terms don't go to zero, then your series has to diverge, right? So it's a different way of saying the same thing as the last one. And I believe we went over this problem, but let me go over this problem again. So here we have this series. You need to be careful. The factorial on this series does not correspond to the 5 in the denominator. In the numerator, the first factor is n plus 1, but in the denominator, the first factor of the factorial is n. And so very difficult to look at that and just by looking at it know what this series is doing, converging or diverging. But if we clean up the terms, the general term of the expression, the general term of the series, then it makes things a little bit easier. So n plus 1 factorial means that you have n plus 1 times n minus 1 times n minus 2, but because we have an n factorial on the bottom, we stop at n, and we have n plus 1 factorial times n factorial. On the bottom, you have 5 over n factorial, and then the factorials cancel out. And so then the terms of your series are simplified to be generated by the simple formula n plus 1 over 5. And so when n is 1, you get 2/5, but when n is 2, you get 3/5, and then 4/5, and then 5/5, and then 6/5, and you can see that your terms are not going to zero. So by that last theorem, we could say the limit as n goes off to infinity of the terms a sub n will be, here's our formula, so then this will be infinity. And therefore, our terms keep getting bigger and bigger. There's no chance for our series to converge. Our sum won't be going to one specific number. Therefore, the series from n equals 1 to infinity of n plus 1 factorial over 5n factorial diverges. Moving on to our next problem, we have it says determining convergence or divergence. And exercises 45 through 58 determine the convergence or divergence of the series, right? So here, when you look at your terms, you have a sub n is given to you by the formula 6 to the n over n plus 1. The terms of your series are given to you by this formula. You should recognize that 6 to the n is an exponential function with a base that's bigger than 1, so that is an increasing function, and that exponential functions grow really, really fast. So the exponential function is going to grow much faster than the linear function in the denominator, and you should recognize just by looking at this that your terms are not going to go to zero, that they're going to go to infinity. And so again, we did this during class. We can take the limit as n goes off to infinity of 6 to the n over n plus 1. But we get infinity over infinity, and so we're going to exchange this for the limit as x goes off to infinity of 6 to the x over x plus 1. And then we can then employ L'Hopital And so then we can exchange this limit for the limit as x goes to infinity of the derivative of the numerator, which you can either look up that limit, or you can natural log and exponentiate to figure out what that limit, what that derivative is. But it turns out to be the natural log of 6 times 6 to the x. And on the bottom, you just get 1. And so now the numerator just keeps growing without bound. And so this is infinity. And so then therefore, since your terms are not going to 0, your limit does not exist. And so your series diverges. Okay, so on this one, this might be where some of you are getting confused as to convergence and divergence, because there are two things that we're talking about, whether they're converging or diverging. The sequence that generates the terms is this sequence right here. A sub n is equal to 4n plus 1 over 3n minus 1. There is no need for L'Hopital in this problem. When we're finding the limit as n goes off to infinity of the terms, 4n plus 1 over 3n minus 1. No need for L'Hopital, because what you have is a rational function where the degree of the numerator is the same as the degree of the denominator. So this limit does exist, and your limit is 4/3. And so then the sequence does converge. As you put in bigger and bigger numbers for n, your terms are getting closer and closer to one specific number, 4/3. But because 4/3 is bigger than 0, that means that you're adding more and more numbers that are getting closer and closer to 4/3. So as you add more and more numbers, your sum is increasing. So this is not 0, right? And so then that means that your series, the series from n equals 1 to infinity of 4n plus 1 over 3n minus 1 diverges. You're going to add more and more terms that are all getting closer and closer to 4/3, and so your sum is just going to keep growing and growing. So again, here we have the natural log of n plus 1 over n. That's the formula that generates my sequence, the terms of my series. You can see that as n gets bigger and bigger, the inside is getting closer and closer to 1, and the natural log of 1 is 0. So the terms do go to 0, but again, that's not enough to get us to get us converging. So we got to be careful with that. Very tempting to want to say that because it makes things nice and easy, but that's not the case. So again, what we might want to do here is look at what happens with the a sub n's. And so the a sub n's, we can use the rules of log here, since there's not a whole lot that I can do that in my mind sparks the idea of maybe we should rewrite this and get the natural log of n plus 1 minus the natural log of n. And if you notice then, once I start looking at my sequences of partial sums, we're going to have a telescoping, and we're going to have a telescoping because the terms are going to start canceling out, right? So for this starts with n equals 1, so S1 will just be the natural log of 2 minus the natural log of 1. S sub 2, you're going to take the natural log of 2 minus the natural log of 1, and then you're going to add to that the natural log of, now n is 2, 3, minus the natural log of 2. Notice here that the natural log of 2's will cancel out. So when we take S sub 3, we only have the natural log of 3 minus the natural log of 1, which then, and we add to that what we get when we put in 3. So when we put in 3, we get the natural log of 4 minus the natural log of 3. Now the natural log of 3's go away, and all we will have is the natural log of 4 minus the natural log of 1. Now the natural log of 1 is 0, so there's no need to carrying that around. So if I look at the s sub 4, we're going to start with what our s sub 3 was, the natural log of 4, and we're going to add the next term. And the next term comes from this formula right here. And so we're going to put in 4, and we'll get the natural log of 5 minus the natural log of 4. And you see how these start canceling. And that is what we mean by telescoping. All the terms start disappearing except for 1 or 2. From there, we can see that s sub n is just equal to the natural log of n plus 1. By looking at, for a pattern, we can see that that's the natural log of n plus 1. Now, so then when we go and take the limit as n goes off to infinity of s sub n, that will be the limit as n goes off to infinity of the natural log of n plus 1. And n plus 1 is going off to infinity, and as you natural log numbers that are getting bigger and bigger, you just get bigger and bigger. So that's infinity. So the terms are going to 0, but it turns out that your sum is not going to specific numbers, just growing without bound. That's what this is telling you. Your sum is growing without bound. And so therefore, the series diverges. Okay, so next we have in exercises 61 through 66, find all values of x for which the series converges. For these values of x, write the sum of the series as a function of x. So what we can see here is that our variable's in the exponent right there. And so then our base is x minus 2 over 3. And so then what this looks like is a geometric series. But the base is not, the base is x minus 2 over 3. So for different values of x, you will get a different sum. But from geometric series, this will only converge if your common ratio is going to be this x minus 2 over 3, is between -1 and 1. And it's not including, I made a mistake there, we're not including, it has to be bigger than -1 and less than 1. So now we have this inequality. If we multiply both sides by 3, we get -3 is less than x minus 2, but it has to be less than 3. So as long as we choose x's so that x minus 2 is between -3 and 3, then our common ratio will be between -1 and 1, and our series will converge. So adding 1 to both sides, you get -1 needs to be less than x, which needs to be less than 5. Adding 2 to all 3 sides, -1 has to be less than x, which has to be less than 5. And so as long as you choose x's in this interval, your series will converge. And what will it converge to? Well, we know that too. We know that it will converge to the first term, and when we put in 0 in for n, your first term will be 5, all over 1 minus the common ratio. And your common ratio is x minus 2 divided by 3. The raised, no raised, just all over 1 minus the common ratio. And so that's what it's asking for. For these values of x, write the sum of the series as a function of x. And what we have is a value of x. And so then again, what we might want to say is this only happens when -1 is less than x, which is less than 5. So for x is between -1 and 5. So that finishes up this section. The homework from this section you already knew. There it is. And we will move on to section 9.3.